the midpoint rule. I would like to recall that we already did this when we did approximation of areas using Riemann sums. So in this case, we are going to approximate the area under the graph y equals fx on the interval AB using n subintervals with the midpoint as the representative point in each subintervals. Again, delta x is equals to b minus a over n. And here's the graph of the function. Okay, don't forget the height is the midpoint. And the midpoint of each interval is the average actually. So it is x1 plus x2 over 2. It means that the midpoint of each of those subintervals a plus I delta x and a plus I plus 1 delta x is the average. So it is really adding up those endpoints divided by 2, and after we simplify, we get a plus I times delta x plus delta x over 2. Just by taking the average. And here's the approximated area. It's the width times the sum of the height of each one of those rectangles. And we get that. We summarize the midpoint rule. This is again approximation of the definite integral of the function fx between a and b. This is just delta x times the sum of the value of the function of the midpoint of each one of the intervals. So again, delta x is b minus a over n, and the midpoint is the average of the two endpoints, a plus I delta x and a plus I plus 1 delta x. When you simplify, you get a plus I plus half times delta x. Example. Let's use the midpoint rule with n equals 4 to approximate the integral of fx dx between 1 and 3. And we'll try to do an analysis on the x. Delta x is 1/2. Here is the subdivision. We are checking that indeed we have 4 subintervals. And here's the midpoint. We can do the average of 1 and 1.5 and we get 1.25. You can just add the endpoints, divide by 2. And here, to get this point, you can again average 2 plus 1.5 divided by 2, or you know that the difference has to be 1/2 from the first midpoint. So if the first midpoint is 1.25, this is going to be 1.75. And here we will do the same. You can average or add 0.5 to 1.75, whatever you like. And we get this point here. Now let's just write the rule. The rule is just now telling me that m sub 4 is 1/2, which is the width, times f of the first point plus f of the second, f of the third plus f of the last point, which is 2.75. Here is a slightly different approach. We can also use the tangent lines to the curve at each midpoint and evaluate the sum of the area of each trapezoid. For example, here is a subinterval, and the midpoint is the red point there. And what happens when we take tangent line? You can observe that the two little triangles, the blue and the yellow, are exactly the same. It's easy to see because both of them are right triangles, Both of them has exactly the same angles, and both of them has the same length of the all three sides, because I would recall that the red dot is the midpoint. It means that the two triangles are exactly the same area. So if you take this little yellow triangle and replace it by the little blue triangle, you will get a trapezoid. So another way to actually view this is really the sum of areas that are actually trapezoids. We summarize. Here is the midpoint rule, which can be viewed again as trapezoidal using the tangent line at the midpoint, or just using directly the height of each one of a rectangle to be the value of the function at the midpoint. And here's the trapezoidal rule. Error bounds for the midpoint and the trapezoidal rules. An approximation has some error, which is the difference between the exact and the approximated values. We need to bound the error, meaning to show that it does not exceed some value. When the bound gets smaller, the approximation gets better. Here are the error bounds for the midpoint and the trapezoidal rules. Let the second derivative of the function in absolute value be less or equal than k sub 2 for all x's between a and b. Then e of mn, which means the error bound for the midpoint with n sub intervals, and e of t sub n, which means the error bound for the trapezoidal rule with n sub intervals, are given by the following. The error for t sub n is less or equals to k2 times b minus a to the power of 3 over 12n to the power of 2. The error for the midpoint with n sub intervals is less or equals to k sub 2 times b minus a cubed over 24n to the power of 2. You can see that the error of the midpoint rule is half the error of the trapezoidal rule. Example. Let's find the error bound for the trapezoidal rule with n equals 100 for the integral between 1 3 of 2 sine of x to the power of 2 dx. First, we are going to just use the formula with b equals 3, a equals 1, and n equals 100. Now we are going to bound the second derivative of the function. Here is the function, here is the first derivative, and here is the second one. We are not going to do small details and really care about x being between 1 and 3, because it's really easy to bound cosine and sine of anything. Cosine and sine of anything can be greater or equals to -1 or less or equals to 1. Also, We're using the fact that if we have something minus something, then in absolute value to bound it, we have to take the absolute value of the first part plus the absolute value of the second part. By this, we make it much larger, most likely. So here it is. The second derivative in absolute value is bounded by 4 times cosine x to the power of 2 in absolute value plus 8 times x to the power of 2 times sine x to the power of 2 in absolute value. Using that, we can eliminate the cosine x to the power of 2 and the sine x to the power of 2 and replace them by 1. And we get this. Now we have to take care of the x to the power of 2. Because x is between 1 and 3, then x in absolute value is between 1 and 3. It means that to bound that from above, which means to get something that is at least as large as this, we have to replace x by 3. And we get that the upper bound of the second derivative in absolute value is 76. It means that this is K2. We will substitute now K2, 76, and we will just do the math. And we get a number which is very, very close to 0.005. What does it mean? It means that the error is not exceeding the number 0.005. Example: find the minimal value of n for which the error for the midpoint rule approximation for the integral from before is smaller than 10 to the power of negative 8. I would like to recall that K2 is 76, and we know that B is 3 and A is 1, so let's use the error bound for the midpoint. We get this. Let's simplify. And I want this to be less than 10 to the minus 8. I need to solve the inequality here, because I need to find n. First, I multiply both sides by 10 to the 8 and by n to the power of 2, and we get that. Using calculator, I'm getting approximation of this square root of 76 over 3 to be almost 5.03322. We get then n has to be larger than 5,332.2, which means that the minimal value of n should be 50,333.